Welcome to this lecture series in group theory. In this lecture, we'll discuss the notion of the conjugation action of a group on itself, and let us recall some relevant things. So earlier we looked at the notion of the centralizer of an element in a group. So suppose we have a group G and an element X in the group, then we defined the centralizer of the element as those things in the group which commute with X, which is of course same as writing this. And we've also defined the center of a group as those things which commute with everything in the group. So that's the center, and we notice that this is a normal subgroup of the group G. So much for the recap. Here are two problems. The first problem I gave earlier as an exercise, but this time I have marked it with a star because I'm going to use it. And the second problem is a very nice problem. Nothing to do with this particular lecture, but this is just for practice. So let us define the conjugation action. Fix a group G and consider the action of the group G on itself, defined as the map phi G cross G to G as phi G comma X, which one can write as G dot X. This is defined as GXG inverse. So this product is taking place in the group G, and this is our definition. And one can check that this is an action. Let me just check one condition. So phi E comma X, which one can write as E dot X, is by definition EXE inverse, which is of course EXE, which is X. So this satisfies the first condition that is required of the map phi for it to be called an action, and similarly you can check the second condition. So that's an exercise. And now we define the notion of a conjugacy class. The orbits under this action are called conjugacy classes. That's the definition. Clearly, since orbits partition the entire set on which a group acts, conjugacy classes also partition the group. What is the conjugacy class of identity? For instance, if E is your element of the group, what is the conjugacy class of it? It's a singleton, it's itself. The only thing in the conjugacy class of identity is this thing. So that's simple example. All right. We define two elements, X and Y, as conjugates of each other if there exists some group element, or rather, let me define it, if they're in the same conjugacy class. Same conjugacy class. So that's our definition of conjugates. You pick two elements in the group, you call them conjugates if they have the same orbit under the conjugation action. And just decoding the definition of an orbit and conjugation action and all that, we see that two elements, X and Y, in the group G are conjugates if there exists some group element such that GXG inverse is equal to Y. So far nothing very interesting has happened. We just saw a nice example of an action of a group, action of a group on itself, and we defined these notions of conjugacy class and conjugates. All right. So what is the size of a conjugacy class? Or in other words, what is the size of an orbit? To calculate the size of an orbit, we use the orbit stabilizer theorem. So again, let G act on itself by a conjugation and fix an element in the group. Then what is the stabilizer of this element? The stabilizer is, of course, those things which satisfy this. Nothing happened. This is equal to G in G, GXG inverse, because G dot X is defined that way, is equal to that, and this is the centralizer of the element X. This is what we recalled earlier. Okay, and this is the notation for, let me use a different color. So this is the notation for the size of the orbit of X under the conjugation action. So this is nothing but the size of GXG inverse, G in G. That's what that notation is, and by the orbit stabilizer theorem, this is equal to the index of the centralizer of X. Right? We just use the fact that this is the stabilizer, and in general, the size of an orbit is same as the index of the stabilizer of that. So the CLX is the size of the orbit, and we see that nothing very complicated is going on. Okay. And now we come to what is called the class equation. This is a very important fact. So fix a finite group, and there are two kinds of conjugacy classes. So here we will talk about conjugacy elements whose, or rather, conjugacy classes of size 1. Oops. This is a problem with the iPad. Conjugacy classes of size 1, and here conjugacy classes of size greater than 1. So there are, of course, only two kinds of conjugacy classes. And let us just schematically, or I don't know what to call it, let us diagrammatically record them. So these are all the conjugacy classes of size 1, these dots, and these are the conjugacy classes of size greater than 1, these blobs. They could have different sizes, of course. All right, so maybe the last one is the biggest blob. Okay, so what we do is, let me call them Z1 up to Z2. Is that a good symbol? Let me think about it. So conjugacy classes of size, yeah, no, that's okay, that's a good symbol. So these are called Z1, Z2, Z3 up to Zr. And let us pick an element here. Let me call that G1. Pick an element here, call that G2. Let me call that X1, X2, X3 up to, let's say, XS. So there are S conjugacy classes of size greater than 1 and R conjugacy classes of size exactly 1. Note that, as we commented earlier, the conjugacy class of identity is has size 1. So R is at least 1. S may be 0. There may be no conjugacy class of size greater than 1, but that's okay. Clearly, the orbits of any action partition the entire group. So if we call this guy, let's call that C1, let's call that C2, C3, and CS. Then since orbits partition the entire group, we have the cardinality of the group is R plus C1 plus mod C1 plus mod C2 plus ... mod CS. Let me write that in the summation notation. So let me write it that way. So that's the cardinality of the group. And why is that? Well, this is one class, this is another class, so we just added the sizes of all these classes and the sizes of all those classes, and that is the size of the group, simply because orbits partition the group. So we have that equation, mod G is equal to this much. And what is the size of Ci? The size of Ci is the size of the orbit of Xi. So this is by what we saw in the previous page. Stabilizer of Xi is the centralizer of Xi. So this is by the orbit stabilizer theorem equal to this much. And this is called the class equation. Oops. This is called the class equation. So it is saying that, okay, so one more thing. Before I box it, what is R? R is those things which have orbit size 1 under the conjugation action. And what are the things whose orbit has size 1? Those are precisely the things which commute with everything. So R is nothing but the size of the center of the group. Right? Something has orbit size 1 under the conjugation action, even only if it commutes with everything, and hence its orbit has size 1 if and only if it lies in the center of the group, and therefore R is nothing but the size of the center of the group. So by that, here I can write cardinality of the center of the group. And that is the class equation. This is called the class equation. And okay, so what does it say? It says that cardinality of a group is cardinality of the center plus you pick representatives of all the conjugacy classes of size greater than 1 and form this sum. So it's some quantity of this sort, which I don't know how to capture in words very well, but just remember this. We've picked representatives from each conjugacy class of size at least 1 and added added this quantity, which is nothing but adding the sizes of the conjugacy class. It's nothing more than that. All right, so we have discussed the class equation, and now let us use it. So we will prove that if P is a prime and G is a group such that size of G is a power of P, a non-trivial power of P, so G is not the trivial group, then its center is non-trivial. So every P group, such a thing is called a P group, a group of size a power of P is called a P group, and we are going to show that every P group has non-trivial center. It's a non-trivial fact. So by the class equation, we have cardinality of G is equal to cardinality of the center plus summation I is equal to 1 to S. I'm just borrowing notation from the previous slide. The index of the centralizer of xi, where xi is a representative of a conjugacy class of size greater than 1. Okay, so what about this quantity? Note that. So note that this is strictly less than the, this is a strict subgroup of the group G. This is a strict subgroup of the group G because if this were equal to G, it would mean that xi commutes with everything, and that would mean it is in the center, and hence its orbit wouldn't have size greater than 1. So this is a strict subgroup of the group G, and hence this is divisible by P. So P divides the index of it. Right? We just use Lagrange's theorem. The size of this divides the size of the group. So the size of this is also a prime power. But since this is less than the size of this is less than the size of the group, if you divide the size of the group by the size of the centralizer, you will get some non-trivial power of P. And therefore, this number is divisible by P. All right, so since each of these are divisible by P, this is also divisible by P. So we see that mod G is congruent to mod ZG mod P. And since P is also assumed to be a prime power, so in particular cardinality of G is divisible by P, we see that cardinality of the center is divisible by P. But the cardinality of the center is at least 1, and why is that? Because identity is lying in the center. So this implies that this is not the same as just the identity element. It has more things in it. In fact, it has at least P things in it because its size is divisible by P. So that's a stronger statement. Its size is divisible by P, but that's anyway clear because once you show it's non-trivial, it is a subgroup of G which by Lagrange's theorem will divide the size of G, and hence its size is going to be a prime power. But the non-triviality is the important part of all of that reasoning. So all right, every P group has non-trivial center. And now let us see a consequence of it. Fix a prime P and let G be a group whose size is P square. Then very interestingly, G is abelian. There is no non-abelian group of this size. Wonderful. Why is that? So there are two cases. ZG, meaning the center of G, is going to be P or P square. Why is that? Okay, all right. Before I even say that, center of G is going to be size 1 or size P square. Why is that? Because if you pick a subgroup of the group G by Lagrange's theorem, the size of the subgroup divides P square. So the size of the subgroup is going to be either 1 or P square. So here we did not use anything about the center. We only used the fact that the center is a subgroup of the group G. But by the previous slide, this goes away. This possibility is not there because ZG is non-trivial. Okay. Thus, so if this is equal to P square, then the center is equal to the group, and hence G is abelian. Because an abelian group by definition is a group whose center is the group. That's a complicated way of expressing the definition of abelianness. But anyway, just think about it if it is not immediately clear. And now the only case that we need to deal with, so assume that the size of the center is P, then what is the size of G mod ZG? ZG is an abelian, is a normal subgroup, so it is legitimate to take this quotient, and therefore the size of this is P. And This implies this is a cyclic group. Every group of prime cardinality is cyclic. You can see that immediately by using Lagrange's theorem. And therefore, by the star marked exercise, G is abelian. So what this argument really says is that this possibility cannot arise. If cardinality of the center is P, then G is abelian, and hence the cardinality of the center is the square of P, meaning the cardinality of the center is same as the cardinality of the group. So this is impossible. The only possibility is that the center is the entire group, and hence the group is abelian. So that's something very nice. All right, so that's all that I have to say. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.